Thank you for the invitation, and thanks so much for all the organizers. Today, I'd like to present our research, the multi-index sequential Monte Carlo ratio estimators for Bayesian inverse problems worked with Cody Law, Neil Watson, and AJ Jasra. Briefly speaking, this is a method use multi-index Monte Carlo to construct ratio estimators where the samples are sampled by the sequential Monte Carlo methods. And by combining all the methods together, we have first a theoretical convergence result to support our method, and another that we can turn the convergence rate for many problems or for more problems from subcanonical to canonical rate. I will discuss this in the following presentations. So before I start, I'd like to discuss briefly show you the structure of my presentation today. So first, I'd like to show you some notations and also discuss what kind of context we are working with, and then move to the multi-level Monte Carlo and also the multi-index Monte Carlo, and then go to the samplers part, where I will introduce two kind of sampler, the Macrochain Monte Carlo and also the sequential Monte Carlo. I know you are all professional in these sections, but I'd like to briefly discuss this and then move to the multi-index sequential Monte Carlo part, which is the mean result, and then show you some numerical results. Okay, so first, we are aiming to find the expectation of this quantity of interest var phi x with respect to the target distribution pi infinity, where x is distributed as pi infinity and var phi x is a real value function. However, we can only approximate this pi infinity up to some finite resolution, this pi alpha, where alpha is the index of refinement. In many cases, people may use L here, indicates the level of refinement. But because we would like to deal with the multi-index case, so we use alpha to indicate this is the index set. Okay. The context we would like to work with is the Bayesian inference. So under Bayesian context, our target distribution becomes a posterior distribution, which is this pi alpha dx given y. This is proportional to the likelihood times the prior. So here, x is the unknown parameter and y is observations. Okay, so this is the notations. The things on the left-hand side is the exact value. Okay, and then on the right-hand side with the alpha as the subscript is the approximation of the corresponding values. So we can see here this f alpha is the approximation of the unnormalized target, and this z and z alpha is the normalizing constant, and this z alpha is the corresponding approximation. Okay, and we use this pi and pi alpha to stand for the normalized target. Okay, so one standard method to solve the problems before is using the standard Monte Carlo estimation, where we assume we can simulate IID samples from this, or not IID samples, we can simulate samples from this target distribution and to construct a single level Monte Carlo estimators like this. This n to the power of -1 times the summation of var phi alpha xi from I equals to 1 to capital N, where N is the number of samples. So the complexity under our context is MSE to the power of minus psi. So this is equivalent to the epsilon notation, epsilon to the -2 psi for psi greater than 1. This is because we have discretization bias, and this is, for example, when we're dealing with the problems related to such as SDE and PDEs, we have this kind of complexity. Well, the canonical rate for the Monte Carlo type of methods is MSE to the power of -1 if we do not have discretization bias. So this is the case when we're dealing with to approximate the integral of an arbitrary function on some specific interval, for example, this 0, 1. Okay, so in the following section, I will show that how we can improve the complexity of this MSE to the power of minus psi to MSE to the power of -1, even we have discretization bias. Okay, so multi-level Monte Carlo methods. So with multi-level Monte Carlo methods, we apply the decomposition. We use the telescope sum from causes level to the finance level capital L, like this. And where L is the finance level of discretization, and we let verify L equals to 0 if L is less than 0. So at level 0, we only have this single term. Okay. With this method, so we expect that the variance of these increments decay with the increase of the level, so that we can use less samples as the increase of the levels. And finally, we have savings in the computational cost. And so the multi-index Monte Carlo method is similar as a multi-level Monte Carlo, but instead we decomposite the value instead of by the increments, we use difference of difference. And here is the difference of difference operator defined like this. Okay, a quick example is when d equals to 2, when we have 2 dimensions, the increments the difference of difference estimator is defined like this. It is worth to note that multi-level Monte Carlo and multi-index method are the same for d equals to 1. So when d equals to 1, we only have the increments. Our focus is on the multi-index method. So let me define the vector of multi-indexes. So we let this both alpha be this a set of alpha 1 to alpha 2 to the d, and where alpha 1 is alpha and alpha 2 to the d is alpha minus the summation of the base vectors. Okay. And here, with the previous discussion, we're now facing 2 situations. The first is that we can sample from a coupling distribution of pi alpha 1 to pi alpha 2 to the d, where the coupling distribution is a joint distribution with marginal being the pi alpha j. And we can sample from this coupling distribution and construct a standard multi-index estimators. And another case is that we cannot sample from this exact coupling distribution. So we have to use approximate coupling and to construct different estimators. So this is the main points that we are considering in the following sections. So samplers and how we can sample from the target distributions. We first construct an approximate coupling. We let this capital pi be the coupling of the prior. So note that this is the exact coupling of the prior distributions. Okay, and we also let this both alpha be the maximum among all the likelihood in different index, and define the approximate coupling like this. This unnormalized target be L times pi 0, L alpha times the pi 0, and this normalized target be capital pi alpha equals to f alpha divided by f alpha 1, where this f alpha 1 is the corresponding normalizing constant. Okay. So we have the first sampling method is Macrochain Monte Carlo, so which is by constructing a algebraic Macrochain such that it is pi invariant. Here is the capital pi invariant, the target distribution, and we can simulate a trajectory from this Macrochain and to construct an estimator. A very commonly used method is called Macrochain testing, and this is by designing a proposal Macrochain app, and we sample from this Macrochain and accept and reject the sample with certain probability defined like this. And another method is a sequential Monte Carlo sampler. Okay, sequential Monte Carlo sampler is a combination of sequential important sampling, resampling, and also the Macrochain Monte Carlo. So we first sample from the target distribution by sampling from a simple distribution. This is the corresponding important sampling part, and then we mutate these samples by macro kernels to decorrelate or jitter the samples along a sequence of distributions where these distributions are converging to the target that we are interested in. And this is the step of sequential important sampling and the Macrochain Monte Carlo. And during the time, we do the resampling when the effective sample size drop down to a certain threshold. In our context, we set the effective sample size be the half of the sample size. And the one advantage of this SMC sampler over the MCMC is that with SMC sampler, we are easily to deal with the problem of multi-mode. And also the second advantage is that the sequential Monte Carlo sampler can give us the normalizing constant without introducing actual computational cost. I mean that we can get the normalizing constant when we're doing the sampling. Okay, let me show the algorithm so that it is easier to see how this happens. And here's some definition of the SMC sampler. We let this HJ be the Fj plus 1 divided by Fj. And this is some intermediate distribution. Where F is the intermediate distribution. This is the friction of Fj plus 1 and Fj. And here we use Fjx equals to Lx to the power of tau j pi 0x. This is the intermediate distribution. Okay, as the tau j increases to 1, we are getting close to the target distribution. This F capital J. Okay, here is pi j, the intermediate distribution, and and this Macrochain kernel here. So this is the algorithm. So we can see that when we do the sampling steps, this 1, 2, 3 is the sampling steps. When we do the sampling steps, we can get this normalizing constant simultaneously. So we do not need to specifically treat this normalizing constant. We can get the normalizing constant at the same time. So that is what I mean, that we won't need to introduce actual cost to compute this normalizing constant. This is very important for us to construct our estimators and to obtain the theoretical convergence results. I will show you later how this is important and why this is important. Okay, now is the MISMC. Okay, the main part. Okay, let me slow down a little bit. So MISMC is multi-index sequential Monte Carlo, which is a combination of multi-index Monte Carlo and sequential Monte Carlo sampler and different estimators. So we have two different kinds of estimators. The first is the self-normalized increment estimator, and this is also works by Cody and AJ. And another one is the ratio estimators. Okay, so let me start from the self-normalized increment estimators. So for the self-normalized increment estimators, we decomposite the summation like this. We use this normalized targets as the difference of difference. Okay, so for the self-normalized increment estimators, we are lack of reverse convergence results under some realistic assumptions. I will show you what these realistic assumptions in the I think next slide. Okay, with this estimators, we can sample from the approximate coupling using SMC sampler and to construct the individual sum like this. And sum of the together, we end up with this pi approximation of this pi alpha. Okay. So the assumption, the results of this estimators are heavily relies on this equality, but this is hard to achieve in reality actually for this constant to convert to 0. Okay. So let's move to the ratio estimators where we can get the theoretical convergent results. So the ratio estimators is obtained by doing the ratio decomposition like this. They decompose this pi var phi being f var phi divided by f1, where f stands for the unnormalized target. And this is approximate equal to the summation of this increments divided by the summation of increments of the normalizing thing, normalizing constant. And we can do the same as before. We sample from the approximate coupling using SMC sampler, but construct a different estimator here. Okay, so here's the steps. Here's some notation here related to SMC sampler, and this is the details of our increments. Okay, and so our ratio estimators can be written like this. Okay, where this I is the index size and N alpha is the number of samples, and this var phi is the quantity of interest. This one stands for the estimation for the normalizing constants. We require that the normalizing constant is lower bounded by the minimum, the another constant. Okay. So note that the estimator for this f for this unnormalized target is unbiased. This is important for us to show that this is theoretically bounded. Okay, so now we made an assumption that the normalizing constant is bounded above and below, and also we made another assumption. This is a kind of standard multi-index Monte Carlo assumptions, but instead of considering the normalizing things, here we require the assumption on the unnormalized things. So this bias is on the unnormalized targets, and also this V corresponding to the kind of variance term is also on the unnormalized targets with respect to the phi distribution. Okay. Here is some theories related to the proof, but I like to skip this and move to the main theorem. Okay. So for the main theorem, we assume 4.1 and 4.2. The 4.1 is the assumption on the constant, and 4.2 is the assumption of the rate. And also, we assume that the summation of gamma j divided by sj. Sorry, I should be clear. The gamma j is related to the cost, the rate of the cost, and this s is the rate of bias, and this beta is the rate for the convergence of the term, the variance term. Okay. And we require the summation of this to be less than or equal to 2, such that the cost at the finest indices do not dominate the whole cost. Okay, and also we assume that this beta I is greater than gamma I. Okay, so with these assumptions, and if we use the tensor products index size, writing like this, there is another plot at a later slides show what is the tensor product index size. Okay, I will show you later. And here is the tensor product index size. If we use this in the index size and following the previous these assumptions, we can end up with a canonical rate. This epsilon to the to the power of 2, given a cost of epsilon to the minus 2. Okay. And another theory is we release the constraint, this constraint, the summation constraint, and we only assume that beta I is greater than gamma I. But here we use a different index size. We use a total degree index size, like this. Okay, the total degree index size is, okay, let me show you the plot after I discuss this theorem. So with this assumption and the total degree index set, we can end up with a canonical rate, also epsilon to the power of 2 with a cos of epsilon to the minus 2. So what is the TD set and what is the TP set? So the TD set, the TP set is all the black circle points along this multi-indices, and the TD set is the point with the red circle. So we can see that with the TD set, we get rid of the more computational complexity points over here, and only use the left triangular point. And it turns out that we may introduce actual bias due to we get rid of this point, but at the end of the summation, we can have the computational saving with the total degree index set, but give the same error requirement. Okay, so we can see this blue circle is the multi-level set, multi-level sets. Actually, we only consider the diagonal here. Let me show you the lemma 4.2, which is the reason why we have the theoretical result. So for the ratio estimators, we have the following inequality. We can bound this MSE by the summation of two terms. The maximum is among the target quantity of interest and normalizing constant. So we can split this mean square error into two terms. You can see that this is similar to the proof of the standard multi-index Monte Carlo. So after this, you can use the standard proof for the multi-index Monte Carlo to finish the proof and get the theoretical result. But with the self-normalized increments estimators, you will introduce an extra cross term here, extra cross term which will mess up the theory. So a short summary here is by comparing the multi-index sequential Monte Carlo with a total degree index set and the tensor product degree tensor product index set, we can see that this TP set heavily relies on the assumption, the summation assumption to achieve a canonical rate. If this is evaluated, we can only achieve the subcanonical complexity because the cost at the final level dominates the whole cost. Okay, but this is often occurred in some high-dimensional problems, which is due to the curse of dimensionality. But with the TP set, we can release this constraint, and we improve the computational complexity for many problems from subcanonical to canonical. Okay. And let me show some numerical results. The first numerical result is on elliptic PDE. This is the standard setting of the PDE, and we solve the PDE using a finite element method. Okay, and here is the standard definition of the Bayesian setting of the PDE problems. Okay, and this is the likelihood, and this is the target distribution. And so first is a 1D toy example, which has an analytical solution like this. Okay, so we do the observation over 10 points, and so our regularity assumption is S equals to 2 and beta equals to 4 and gamma equals to 1. So for this particular problem, the multi-level method has a MSE to the power of -1, and the same to the multi-index, because multi-index and multi-level are the same in the 1D example. But for the single level method, we only have MSE to the power of -4 or 5. Okay, here is a plot. The yellow line is for the single level Monte Carlo, this yellow line. We fit this line, which has a rate close to -0.8. And others these two are MLSMC with self-normalized increments and the ratio estimator. And here we also compare a multi-level Macrochain Monte Carlo with a self-normalized increments estimators. We can say although this multi-level MLMC line has a less small constant than the multi-level SMC plot, but it turns out that probably it is better to use sacrifice some saving in the constant to get a theoretical result. So we don't have theoretical support and a realistic assumption for this multi-level Macrochain Monte Carlo method. Okay, here is an example on the 2D elliptic PDE with a random coefficient. So here we let this AX be a random input like this. Okay, we observe 4 points. This is an observation size, and here's the regularity assumptions. Okay, and also for the multi-level and multi-index methods, we have MSE to the power of -1, the canonical rate, and single method has a MSE to the -2/3. And this is the plot. Okay, a little bit messy here, but we fit all the lines, and the rate is close to -1 over here. So another example is a shame here. It's a little bit shame here that we didn't do an example to show from subcanonical to canonical with a PDE example. Instead, we use a log-Gaussian Cox process model. Okay, this is the citing of the log-Gaussian Cox process model, and here's the likelihood, and this is the approximation of the likelihood, and here's some parameter settings. And for this LGC or LGP models, we have single methods MSE to the power of -9/4, and MLSMC or MISMC with TV set has MSE to the power of -5/4. This is subcanonical. But with the MISMC with the TV set, we can achieve the canonical rate. Okay, and here's the plot. It is clear that this has a worse rate, and we also fit both of the line, and this has a rate roughly -0.6 or 7, I think, and this is close to -1. And also this is log-Gaussian process model. We can also observe the similar performance. Okay, and so in conclusion, that MIS multi-index sequential Monte Carlo with a ratio estimators has rigorous theoretical results under realistic assumptions, because they use the unbiased estimation for the unnormalized increments of increments at the denominator and the numerator. And also another summary is that with this method, under the total degree index set, we can improve the complexity of multi-level or multi-index with TP set from subcanonical to canonical. This can also applied in the higher dimensional PD examples, and also get the canonical rate as long as the theory can be satisfied. Okay, and here's some reference. And thank you so much for your attention. And this is the link for our paper, the archive version, and this is the code in the GitHub. Thank you.